This is a lesson for polar area for BC Calculus. And we're going to start by figuring out a basic geometry formula, but in terms of radians. So if we wanted to find the area of a sector with an angle theta and a radius r, then we would be taking a fraction of the whole circle. And since a whole circle's area is pi r squared, then the area of the sector is just equal to the angle theta divided by the angles in the entire circle. In degrees, it would be 360 degrees, so you would do a portion of the circle over 360, and since it's in radians, we'll say that there are 2 pi radians in the whole circle. So that is a formula for the area of a sector, and if you simplify that formula, you get that theta divided by 2 times r squared is the area of a sector. As we're solving some of the problems in this section, these two trig identities will be helpful, and so I just put them there as a reference. They're not too hard to derive, but we're not going to do that in this video. So to get the concept of polar area, we're going to take a polar curve and divide it up into little tiny sectors using the same concept as finding the area under a curve in the xy coordinate plane by using rectangles. In polar, we'll use sectors, and that's why we need this formula. So if you think of the area of a sector, we'll put that down here, is 1/2 theta times the radius squared. That's kind of the general formula for the area of any sector. And then we're basically going to try to write an expression for the area of one of these typical sectors here. So this curve is r equals f of theta, and the radius of any one of these, with this being theta 1, theta 2, theta 3, theta 4, theta, so the radius of any one of them is f of theta I. And then the angle of any one of these, like this theta here, we'll call any one of these, that angle being delta theta. And the width of any one of these sectors, or the number of radians in each one of these sectors, could be determined by taking beta, subtracting alpha, and dividing by the number of sectors. So alpha being the starting place and beta being the ending place. And if you take, say, a small theta subtracted from a larger theta and then divide that up by the number of sectors, that gives you the width of each sector. So then if I wanted to sum up the area of all those, I would get that the area equals the sum from I equal 1 to n of 1/2. And then theta, in this case, would be delta theta, because we are just doing a little, one little sector at a time, and then we're going to add them all up. And then the radius squared, which is f of theta sub I squared. So that would give me a finite sum for these. So I should say that the area in this whole polar curve is approximately equal to the sum of all these little sectors. This isn't exact because these little sectors have a little bit that's sticking out, or maybe a little bit less, just like the rectangular approximation. But then what will make this get more accurate is if you let the number of sectors go to infinity, then you'll get that the actual area is the limit as n approaches infinity of 1/2, you can pull that 1/2 through, the sum I equal 1 to n of f theta sub I squared, and then we can put the delta theta second, because then that will help us make the leap to thinking of this as the integral from alpha to beta of f of theta squared d theta. And that works as long as alpha is smaller than beta, and that when you subtract the large angle from the small angle, that you are only within 2 pi. So that's just meaning that the interval that you're integrating across has to be between 0 and 2 pi. You can't go, say, 0 to 4 pi. And it also there's also an additional clause that the radius has to be, the function is continuous and non-negative on the interval. So these radii have to be positive. And there's actually a little technicality that it's okay if they're negative, but they just all have to be negative. So you can't integrate over a region where the radii are both positive and negative in your angle values. So let's look at some examples. And the first one we're going to look at is to find the area of one petal of the rose curve given by 3 cosine 3 theta. And so we know that we'll use the formula that the area is equal to 1/2 the integral from alpha to beta of the radius squared d theta. And in this case, the radius is 3 cosine 3 theta. And so the area will be 1/2 the integral from, we need to figure out what these values are. We'll do that in just a second. The function, though, will be 3 cosine 3 theta squared d theta. And then finding these values is a little bit tricky. Depends on the problem, but to find them in this case, we would just take 3 cosine 3 theta and set it equal to 0. And so then this is asking, when does cosine 3 theta equal 0? Or when this would be at pi over, we could say negative pi over 2 and positive pi over 2 plus 2 pi k. And then if you divide that by 3, you'll get negative pi over 6 and positive pi over 6 plus 2 pi over 3k. But we don't really care about the 2 pi over 3 part. So this is negative pi over 6, and this is positive pi over 6, and so this is negative pi over 6 and positive pi over 6. So if we do the integral out all the way by hand, then we would need the integral, or 1/2 the integral. We could take out 3 squared is 9. So we could put a 9 out here, and then the integral from negative pi over 6 to pi over 6 of cosine 3 theta squared d theta. And this, you need a trig identity to get rid of the squared in that, and that was the identity that I gave you on the first page. Since it's cosine squared 3 theta, then this integral can become 9/2 times the integral of pi over 6, negative pi over 6 to positive pi over 6. And this gets replaced with 1, and if it's cosine, then this is a plus cosine of, and what goes in here is always 2 times whatever is in here, so this will become 6 theta. And then you can take this 2 and put it out in front, so you'd get 9/4 times the integral of negative pi over 6 to positive pi over 6 of 1 plus cosine 6 theta. and then 9/4. The antiderivative of 1 is theta. The antiderivative of cosine 6 theta would be sine 6 theta, and then you need a 1/6 or an over 6. And then the derivative of sine is cosine, so this will just stay plus. And then if we evaluate that, and we put pi over 6, and then if you substitute in pi over 6, you get the sine of pi, which is just 0. So that's 0. And then if we put in minus and a negative pi over 6, we also get 0 for the sine when we substitute in negative pi over 6. And so we get 9/4 times 2 pi over 6, which is pi over 3. So that ends up being 3 pi over 4. Whew. All right, I'm going to pause and do a new video for one last example.